How's it going? Hope you all are doing well today. All right. Did you have any questions before we start? No questions? Um, I believe so, yes. Wait, 15th? That's a Sunday, isn't it? Is it the 12th? I think it's the 12th. But if you need a little bit longer, I mean, that's fine. But yeah, I believe I said the 12th for this class. Okay. Yeah, honestly, I remember one class was the 16th, but I think that was my Monday, Wednesday class was the 16th because they're a little bit behind us. So, uh, yeah, that would put ours at the 12th. Okay. So, I'm going to continue with section 7.2 today. Um, Last time, we talked about just finding probabilities based on z for the most part, although we did one example where we looked at an actual application where we had to convert the x value into a z-score and then find the value from either the table or the calculators. Um, let's look at 38 on page 375. The reading speed of 6th grade students is approximately normal, with a mean speed of 125 words per minute and a standard deviation of 24 words per minute. Okay. This is the question A, and I wanted you to skip this on 37 in the homework, but question A is just draw a general model that describes the reading speed of 6th grade students. We don't have to go into that where we draw a model. We're just going to look at question B, C, and D, and E. So, just basically skip A. Okay. Find and interpret the probability that a randomly selected 6th grade student reads less than 100 words per minute. So we want the probability that they read less than 100 words per minute. Okay, so that means our data value x is 100. Okay, where do you have mu and sigma? And so we can use that to calculate z. Again, the formula for a z-score is x minus mu divided by sigma. So we plug in, x is 100, mu is 125, and sigma is 24. And so that'll give us negative 25 over 24. So negative 1.04. Okay. So that gives us a z-score that we can work with. Now, we go ahead and draw our normal distribution, our standard normal distribution. We know 0 is in the middle, and negative 1.04 is slightly to the left of 0. And we have to decide which side of this that we need to shade the area under the graph. We're going to shade to the left or to the right based on the question. There is one key thing here that's going to tell us which direction that we shade in. And that'll be in the question. It asks us the probability that a randomly selected 6th grader would read less than 100 words per minute. Well, what we've calculated is the z-score for 100 words per minute. So less than that would be everything to the left. Okay. How's it going? In this case, we want to identify our lower bound and our upper bound, and that'll be useful for the purposes of the using our calculators to solve this problem. The lower bound, since it continues all the way to the left, we can use negative 10 as a lower bound. And an upper bound, the right boundary, would be negative 1.04. So we have our two boundaries, and we know for a standard normal distribution that we'll use mean 0 and standard deviation 1. Let me do this on the 36. Let's go second data, arrow to distribution, down to normal CDF, mean 0, standard deviation 1. For a lower bound, we said negative 10. For upper bound, 1.04. Enter that in. Okay. Let's try again. I don't know what I didn't like. Oh, I may have mishit a negative instead of a decimal point. Anyway, so we get a value. I'm going to double check that. Sorry. The value did not make sense. Negative 10 and negative 1.04. Oh, I know what I did. I left off the negative on 1.04. There we go. 0.1492. Okay. One thing I wanted to point out there is when I got a result of 0.85, this is where the graph helps us. Okay, we see in our graph that this is the area here is definitely less than half, because halfway would be right at 0, and that would be a 0.5 probability if we got to halfway. So the fact that I initially came up with an answer of 0.85 was way too large for the area that we're looking at. And probably what I did is I left off the negative from the 1.04 and made it a positive 1.04, which is what led to that error. But there's one way that we can kind of check our work as we go. If we understand exactly what we could expect here. We know half of this area is 0.5. So in this case, recognizing that the shaded area is less than half of the area, we know that we should get an answer that is a pretty good distance less than 0.5 based on that. And we see the actual answer is actually 0.15 for thereabouts. Anyway, so that's we want to pay attention to what we're doing, but also be able to recognize when an answer is incorrect or does not make sense in the context of the problem. That's always helpful. I mean, it's best not to make mistakes in the first place, but it's also important to know that we are not perfect people. Okay, part C, find and interpret the probability that a randomly selected 6th grade student reads more than 140 words per minute. Okay. So whatever value they give us here, this is our x value, so we'll use x equals 140 because the mean and the standard deviation are certainly given to us in the original description of the problem. Okay, so z is x minus mu over sigma. X is 140, mu is 125, and sigma is 24. So if we subtract, that's 15 over 24, which is 0.625. So we'll do 0.63. Okay. So 0.63 is we know 0's in the middle, and this is a positive number. So we'll go a little bit to the right of 0, 0.63. And again, if we want the region, we want the probability that's more than 140, that means we'll shade to the right. And the previous one said less than, so we shaded to the left. Here we see more than, we'll shade to the right. The only other outcome is that it may say between, and we'll have the area between two values. What's our lower bound and our upper bound in this case? Any idea? Okay, the boundaries, or the bounds, as we call them, these are the edges of the shaded area that we just sketched in. So we notice that the left edge, the lower edge, is at 0.63. And the graph continues to the right from there, so we'll say it goes up to 10. Now, technically it goes much higher than 10, but it turns out, as far as the calculators are concerned, 10 is as good as anything else. And I think it's a little bit easier to do than trying to type in infinity or 1 times 10 to the 99th, or whatever highest value the calculator accepts. 10 is perfectly acceptable because it still gives us all the same values. Okay. Now we can go into our calculator. Second, data, arrow right, down to CDF. Mean is 0, standard deviation is 1, so we just press enter. Now for the bounds, we put 0.63. And actually, you don't have to put the 0 point, you just put a 0.63 if you like. I'm just being formal. And then 10 for the upper bound, and then calculate. And we should have our probability, 0.2643. Okay. So, what we can conclude from that is that there's a 26%, a little bit better than 26% chance that a randomly selected 6th grader will read more than 140 words per minute. Okay. Part D. Find and interpret the probability that a randomly selected 6th grade student reads between 110 and 130 words per minute. Words per minute. Alright, now when it's between two values like this, we did go over one example very quickly on last Thursday, but each of these are considered X values. Okay, these are data values, 110 and 130 words per minute, because they're measured in words per minute. So all of our data values in this problem are measured in words per minute. So that means for x equals 110, we have to calculate z, and for x equals 130, we have to calculate z for that one as well. So we'll need to calculate z for each of these numbers. And again, z is x minus mu over sigma. So for x equals 110, we'll plug in 110 for x. Mu is 125. And sigma is 24. And then for 130, minus 125 over 24 for the second one. This is negative 15 over 24, which is negative 0.63. And this one will be 5 over 24, which is not as exact. We'll make that one 0.21, positive 0.21. Okay. Now again, notice that each of our z-scores are being rounded to 2 decimal places, and the reason that we're doing that is so that we could look them up using the textbook instead of the calculators. Okay. Drawing our graph now. We have negative 0.63 and positive 0.21. And we want the area between those two, or the probability that x or z falls between those two values. Okay. Now the nice thing here is that for our lower and upper bounds, it's actually the same as these two values we just found. Our lower bound is negative 0.63 and our upper bound is positive 0.21. Okay. So we go to the calculator, second data, normal CDF, 0 for the mean, 1 for the standard deviation, negative 0.63, and then 0.21 for the boundaries. And calculate. It gives us 0.3188. So almost a 32% chance that a randomly selected 6th grader will read between 110 and 130 words per minute. That's fine, Haley. Go ahead. Mm-hmm. Now in B, we notice that the graph just keeps going to the left. But we need to use something as a lower boundary in this case. And so what I've kind of decided is that negative 10 is sufficient. And it's not that I decided negative 10 is sufficient. What I've found is that negative 10 is sufficient. So, I mean, we could put a larger negative number there, but negative 10 will do just the same as far as the outcome that it gives us. But basically, it keeps going to infinity in that direction. And so we just need to use a number for the calculator's purpose. Okay, so negative 10 will work because the probability that something will be 10 standard deviations below the mean is effectively 0. Okay, so it's not like we're leaving out any potentialities there. Same thing on the high side in C. On the upper bound, again, the graph just keeps going, so we can just do 10. Yeah, the calculator, the 36 by default will put 1E99 there, so if you just want to leave that alone, that would actually be more accurate, but I mean, theoretically more accurate, but as far as what the calculators display, it's actually the same level of accuracy, whether we change that to 10 or we leave it as 1E99. Or 1 times 10 to the 99th power. So if you just want to use 10, that's fine. Especially on the 83s, you're going to have to put something in there by hand. So I would recommend 10 than trying to do 1E99. Okay. Okay, so let's do problem 42, and I'll use the 83 for 42. General Electric manufactures a decorative, crystal clear 60-watt light bulb that it advertises will last 1,500 hours. Suppose that the lifetimes. Sorry, that was not mu. Suppose that the lifetimes of light bulbs are approximately normally distributed with a mean of 1,550 hours. That's our mean. And a standard deviation of 57 hours. So that's our mean and our standard deviation provided. And again, we'll start with question B here. Actually, we could begin with question A. What proportion of the light bulbs will last less than the advertised time? Okay. Well, what's been advertised to us is that the light bulb should last at least 1,500 hours. Okay. So this means less than 1,500 hours. Now, that means that basically we want the probability that a light bulb will not meet the company's statement. And there's different ways that we can ask this question, and I'll add on an extra question at the end of this problem where we look at it from a different way. Excuse me. Let's see, so less than 1,500, that means that's our x value, 1,500. So we'll let z equal x minus mu divided by sigma. Okay. So it gives negative 50 over 57. Sorry. And if we divide that, we get negative 0.88. Okay. So that's our z-score for 1500 hours. Now, let's see, that'll work. I'm going to draw a graph over here. I encourage you to draw a graph for each of the problems that we work. We know 0 is in the middle. Negative 0.88 is to the left of 0 because it's negative. And we want the probability or the proportion that will last less than the advertised time, which is less than 1500 hours. So that means less than will be the area shaded to the left. Okay. So this is what we're working with, and we look at this and we see, okay, what is the lower bound and what is the upper bound? What can we use for the lower bound here? Lower we'll use negative 10 since it keeps going to the left. And for upper we'll use negative 0.88. Okay. Now on the 83s and the 84s, we start off by pressing second vars and arrow down to normal CDF, which is option 2. Press enter. We put the lower bound first, negative 10, comma, the upper bound, negative 0.88, comma, then the mean 0, and the standard deviation 1. Now the mean and the standard deviation are different here because we went to a standard normal score with the z rather than leaving it as an x. We press enter and we get a probability or a proportion of 0.1894. So about 19% of the light bulbs will last less than the advertised time of 1500 hours. Okay. With a little practice, these problems can go pretty quickly, although we don't necessarily want to hurry because we want to make sure we pay attention to all the details and make sure we're entering everything correctly, of course. But again, this is something that does require practice, so I hope y'all will get a chance to work on a number of these things. Alright, let's keep looking at problem 42 here. And let me just write down the mean and standard deviation again. Mean is 1550 and standard deviation was 57 hours. So part B, what proportion of the light bulbs will last more than 1,650 hours? Okay. So lasting longer than 1,650 hours, that's again our x, or data value. And so we'll use that to calculate z. So that's 1650 minus 1,550 over 57. So that will be 100 over 57. So it's 1.75. That's just sad. I'm sorry, guys. That's no good. That's not a great bell curve. We can do better than that. Doesn't have to be perfect, but I'm trying to set an example here. Anyway, z equals 1.75. We know right in the middle is 0, so 1.75 is a good ways to the right of that. Now, do we shade to the left or to the right of 1.75? To the right? Yes. Yeah, we know it's more than 1650, and then we can say, okay, the more than would be to the right. If it had said less than, then that would be to the left. Now, again, we could use language such as at most or at least. We have to be sure we're comfortable with those also. Okay. For our lower bound, for the left edge of our shaded area, that's 1.75. And for our upper bound, because the shaded area keeps going to the right, we'll use 10 as the upper. Now we'll go into the calculator. Second vars, pick option 2. And we'll enter lower and upper first, 1.75, comma, 10, comma 0, comma 1, close parentheses. And so 0.0401. So roughly 4% of the light bulbs will last more than 1,650 hours. Okay. All right. Part C. What is the probability that a randomly selected GE crystal clear 68 watt light bulb So descriptive. Will last between 1,625 and 1,725 hours. Okay. Again, because they give us two values here, these are both data values because they're both measured in hours. In this case, that's the data type that we're looking at is the number of hours that each light bulb actually lasts. So, for each of these numbers, 1625 and 1725, we'll have to calculate different z-scores. So x minus mu divided by sigma. So we'll fill in 1625 minus 1550 divided by 57. X here is 1725, but otherwise the other numbers are the same. Okay. So here we will get, let's see, that is 75 divided by 57. And this is 175 divided by 57. So we get 1.32 and 3.07. So whenever they give us two data values, we have to calculate a z-score for each of those. Especially, and this is really only in the case where we find the area between that we have to worry about this. So especially if we're finding the area between two values, we know that we have to convert both of those to different z-scores, as we've done here. So creating a graph, 1.32 certainly is to the right of 0, and then 3.07 would be way over here. And we want the area between, so we'll shade the area between those two numbers. Now our lower bound in this case is 1.32, and our upper is 3.07. These are pretty straightforward because we do have the area between. So on our 83s, the second vars, option 2, we enter in the lower boundary 1.32, comma, our upper boundary 3.07, comma 0, comma 1, and then close parentheses. So we get 0.0923 as our probability of that occurring. So again, that means a 9.23% chance that a randomly selected light bulb will last between 1,625 and 1,725 hours. Okay. Now, I want to go in a little bit different direction here than what this problem initially said, but we still need to keep in mind the original mean and standard deviation that were given to us, which were 1,550 and 57, respectively. Those are hours. Your calculator keeps giving you 0. Are you making sure to use normal CDF, not PDF? Although I'm not sure if that would change it. Let's see, we did 1.32 and then 3.07. The only way it should give you 0 is if you enter the same number for both the upper and the lower bound. Oh, but we don't have to enter that. If we change to a z-score, then we just use 0 and 1 for the mean and standard deviation. If you go back, if you notice what I did, I didn't change those values at all. Just leave it 0 and 1. That's why you're getting 0. Now, what you're doing is entirely, it's correct, but we wouldn't change our data value to a z-score instead. The reason I don't teach it that way is because it makes it difficult for students to figure out the right edge or the right bound and lower bound if it keeps going beyond the value. It's much easier to predict what we can use there if we've normalized it or standardized it to the z-score scale. But you could do it the other way. But you have to change all the numbers, or not change all the numbers, I guess, is what the issue is. But hopefully that helps. Now, not so good. Don't worry about it. What guarantee? So we remember that this company said that their light bulbs would last at least 1,500 hours, and we discovered that even at 1,500 hours in Part A, it was about a 19% of the light bulbs would last less than that. What guarantee for hours lasted would the company have to give so that only 10% of the light bulbs last less than that amount of time. Okay. And basically, this turns the question around. We're actually looking for how many hours that the company would say the light bulbs would last at least. No, they said 1,500 in their PR, but we already found in problem A or 42A that 19% of the light bulbs still stop working before that 1,500 hour mark on average. So what if we wanted to reduce that to 10%? What hours, or how many hours would we have to say the light bulbs would last at minimum in order for that to be true? Only 10% would fall below that level. Okay, so when we say 10%, in this case, it's essentially we're talking about percentile. Okay. So essentially, we want to find the 10th percentile for the lifetimes of these light bulbs. Okay. Now we have a separate operation in the calculators that allows us to find this. Okay. So essentially, we need to figure out let me draw a graph. We know the mean is 1550, and we need to figure out an x value so that the area left is 10%, or 0.10. Okay. And this is a little bit tricky, but it uses basically we're reversing the process that we just did. We know what the area or the probability needs to be. We've pre-selected that, but we need to figure out what value that occurs at. Now in the calculators, we have the normal, no, the inverse normal, sorry, which, let me see what they say, second vars, yeah, I and V normal, yeah, the same on this one, I think. Yep, that's option 3 here, is inverse normal. Okay. Now one thing, and I mentioned this before, but I uploaded a formula sheet to Canvas, or, well, it's formulas and calculator instructions, which I think is useful. Let me flip over real quick. Sorry. In our files, formula sheets and calculator instructions, It's chapter 7, 8, and 9, formulas and calculator instructions. That's where we're at now. Okay. So here's our normal CDF that we were talking about, z equals x minus b over sigma. Then on the calculator, you do normal CDF, we have the left edge, the right edge, 0 and 1. Now finding percentiles, this is what we're looking at. Now on the 83s and 84s, it's second vars and select inverse normal. But specifically on the 83, we'll want to enter inverse normal, and then the percentile, and then the mean, and then the standard deviation. Okay. The other two calculators will prompt us to find those things, so we don't have to worry about it as much when we get to inverse normal. But on the 83s, we have to make sure we put them in the right order, otherwise it's not going to give us the right answer. It is problematic in that regard. Okay, let me close this out. There we go. So we use inverse normal. Okay. Now, sorry, I want that. It's lighter on the left-hand side for some reason. So we had second data, go to distributions, and we want inverse normal, which is our third option here. Press enter. Okay, and it says the area, so we do 0.10, 10%, 10th percentile. For our mean, we'll do 1550. And for the sigma, standard deviation, that is 57. We calculate, and we get a value of 1476.95, so it's about 1477 hours. Okay. So again, with the inverse normal, we second data, right to distribution, arrow down or click on 3 for inverse normal. And then we enter the area to the left. Again, when it says area, it means area to the left, which we said was 0.10. So we entered 0.10. We entered our mean, 1550, and our standard deviation, 57. We did on the calculate, and that's where we got our answer, 1,477 hours. Okay. It's pretty easy on the 36 axis. Let's look at the 83s. As usual, it's slightly less easy on the 83s. We do second vars, go down to inverse normal, but again, here we have to enter our terms separated by commas, so we do the area left first, or the percentile, 0.10, comma, the mean, 1550, comma, standard deviation, 57. And then we notice that we get the same result, 1476.95, so about 1477 hours. Okay, now the only thing that remains is the textbook. So we do need to figure out how to do this in the textbook, and it turns out using the textbook instead of the calculators, it's a little bit more complicated. Specifically, we're looking at the tables here. Now, we want to find z where the area left is 0.1000. So we look at our table here. Now, sorry. I'm just going to lose my place. When we are looking this up, we're actually trying to find the z value. So we're actually picking a value in the body of the table here and then backtracking to get the z-score. So we need 0.1000. Looks like we're kind of in the right area here. Over here. So right here we see this is the closest we can get to 0.1000. So this is slightly more than 10%, 10.03%. Okay? And so what we want to do is we want to look up that z-score. So we go to the left. This is negative 1.2. I know you can't see that. If we go up, it's the next to the last column, so it's negative 1.28. Okay. Now the textbook will give us a little bit different answer than we got from the calculators because it won't be quite as exact. But again, we're basically doing a reverse lookup on the table. And we start with the number in the body and we backtrack to get the number on the edges, the z-score. So we think z equals negative 1.28. This is the closest we can get to 0.1000. Now, with that in mind, that's our z-score. Then we know x is equal to sigma times z plus mu. Now, this formula is basically the same formula as the z-score, z equals x minus mu over sigma, but we've taken that same equation and solved for x instead. Because this time, we're given the mean, 1550, and standard deviation 57, and we just found z was negative 1.28. So we can plug in all three of those values. I really recommend that you have a calculator for this stuff because the textbook's way harder. Alright, so if we want to calculate that, let's see, we have 57 times negative 1.28, and we add 1550 to that, and it gives us 1477.04. So it's actually pretty close. It's just on the opposite side of 1477. So just like the with the calculator, we do end up with the same number of hours here, but it's a little bit more of a convoluted approach to finding it, so I really hope everyone has a calculator that they can use to solve this. The table will work, but it's a little problematic though. Find my place again, sorry. Oh, I'm almost right on track. Okay. Anyway, let's see. Let me just go ahead and give you homework. I think that'll be a good stopping point today. Go ahead and look at number 39. This is page 375, sorry. Number 39, 41, and then also look at 47A and 49A. Now those last two problems are problems on percentiles, and so it's this reverse lookup like we were just talking about in this last problem. So go ahead and try those out using the inverse normal function of the calculator, or like we did this last part here. Alright, and that wraps up chapter 7 for us, so next time we will be starting chapter 8. Alright, are there any questions? Oh. Send their project in a blank paper or into the answers on the page. I got you. Sorry, it took me a second. Please, my first thought was please don't submit a blank paper. I know that's not what you're asking. Yeah, if you just want to put the answers down on paper and then just make sure you number them, of course, but that'll be fine. Yeah. Okay. So you all take care. And have a good rest of the day, and I will talk to you again Thursday. Bye.